Welcome to Group 4's Refrigeration Presentation. So Machine Chillers has developed a cooling system which is based on the vortex tube, and Burdell Inc. has hired us to provide an independent review of the system. And in week 1 we looked at the steady state, where we characterized the motor, compressor, and the vortex tube, and we analyzed the steady state response of the refrigerated load. And then we determined the discrepancy between theoretical and experimental insulation resistance of a styrofoam block. And we did uncertainty analysis. So the equipment started with the pump, which is powered by, or the compressor, which is powered by the engine, which pumps into an air-to-air heat exchanger, which goes into the vortex tube, which splits the air into hot, which goes out on the left side of the diagram, and cold, which goes into the load and then exits on the right side. These systems were the pressure regulator, heat exchanger, accumulator, vortex tube, and the insulated load. And we used pressure sensors, thermocouples, and flow meters. And we collected data at various motor voltages of 0, 0.5, 1, 1.5, and 2 volts. And we made sure to take the offset values and make sure that everything was at ambient before we got those. So, some of the results. We're going to characterize motor voltage to pressure. We're going to characterize pressure to vortex tube outputs. We're going to characterize the block response to the vortex cold side outputs. So, the first one, we characterize the motor voltage to pressure relationship. And the data shows a nonlinear relationship between these. And which is decreasing at higher voltages probably due to the inefficiencies in the pump. And from the York fit, there was around, if you use a linear relationship, it's about 2.0923 e to the 5 times the voltage plus 1.2661 gives the pressure.
After this, we characterize the vortex tube outlet temperatures versus the pressure at the inlet. The temperature for the hot outlet has a linear relationship with inlet pressure, but the temperature for the cold outlet has a non-linear relationship. Fitting the data to a quadratic seems to produce a better fit for the data, even though the true relationship is actually not quadratic. On top of this, the cold temperature stopped decreasing with time, meaning that the vortex tube's efficiency at the cold outlet goes down with increasing pressure. From the graph, this pressure where the temperature stops decreasing is about 45,000 pascals, or about 50 psi. We did this same analysis for the mass flow rate at the outlets versus pressures at the inlets. For the hot mass flow rate outlet, there was a nonlinear relationship. Again, a quadratic fit was a lot better than a linear fit, but that relationship is likely not quadratic. But for the cold mass flow rate at the outlet, there was a very linear relationship.
During week 1 of the lab, we characterized how well the styrofoam insulated the aluminum block while in steady state. Our goal was to compare the theoretical and experimental Q ambient and our insulation values to see how well the system follows theory. Because we are in steady state, we can assume that the heat transfer of the load is equal to 0. This allows us to calculate the heat transfer to the environment using the first highlighted equation. To find the theoretical thermal resistance of the styrofoam block, we used the second highlighted equation. The dimensions of the styrofoam block were measured to find the surface area. For the theoretical or insulation term, we assumed that the styrofoam block was enclosed. For the experimental calculation of Q ambient, we used the following equation. Using this equation and the theoretical Q ambient equation found in slide 8, we were also able to find an experimental thermal resistance of the styrofoam. The table below lists the results of the theoretical and experimental Q ambient terms. Theoretically, Q ambient had a positive nonlinear relationship with motor voltage. However, experimentally, the relationship between the two is hard to characterize. This relationship may be a result of the equation used to calculate Q ambient. The equation involves the temperature from station 4C, which was determined to have a nonlinear relationship in slide 6. As a result, the experimental Q ambient seems to follow the same trend. Another difference is that the experimental Q ambient was larger than the theoretical Q ambient. The cause of this was due to the difference in the theoretical and experimental R insulation terms, which are discussed in the next slide. Taking a look at the experimental thermal resistance and thermal conductivity of the styrofoam, it is apparent that these values change as the motor voltage changes. It is also apparent that these values do not match the theory at all, with the R insulation values being much smaller than theoretical and the thermal conductivity values being much greater than the theoretical. Except for a motor voltage of 0.5 volts, R insulation has a direct relationship with motor voltage, and K insulation has an inverse relationship with motor voltage. From these results, we can conclude that the styrofoam insulation works better as pressure increases. However, there is still a discrepancy between the theoretical and experimental R insulation and K insulation terms. From week 1, we can conclude that the modeling assumptions do not represent the system well. The main discrepancy arises from our assumption that the styrofoam covers the entire aluminum block. Because the aluminum block is not fully enclosed inside of the styrofoam, there is more heat transfer to the environment than expected. This could be from convection due to the air in the lab. Another discrepancy comes from the location of the thermocouple on the aluminum block, which is located on the top of the block. This location may not be giving us an accurate representation of the system performance. Placing the thermocouple at the center of the block, where it is further enclosed inside the insulation, may make the theoretical and experimental Q ambient values more related.
These are the calculated combined uncertainty values for the experimental enthalpy rate for each nominal PSI value. Air propagation analysis was used to account for uncertainty from the cold mass flow rate T5 and T4 cold. These are the calculated combined uncertainties for the heat transfer rate due to ambient heating. At steady state, the heat transfer rates due to air and ambient heating should be the same. These values were calculated using the theoretical R insulation value. However, notice that the uncertainties of the ambient heat transfer rate and that of air don't overlap. This means that the experiment fails to account for some factors that are leading to this discrepancy, such as the specific heat of the air in the experiment not accounting for humidity in the room.
For week 2, we will first have to recollect the offsets for each sensor, because the offsets likely changed from the last time we collected data. For this week, we will take data for all stations, starting at ambient temperature, and then ending when the data reaches approximately steady state. We will do 2 of these transient tests. For the first test, we will be using a pressure of about 40 psi found from the motor's pressure-voltage relationship discussed previously. The voltage that produces this is about 1 volt. The second test will be using a gauge pressure of 80 psi using the building's air. After this, we will compare the performance of the system for these different tests, such as the steady state values and rise times of the load temperature. We predict that we will see a lower temperature of the load and a longer time to reach steady state for a higher input pressure, but will likely see a less drastic change from the lower pressure due to the decreasing efficiency of the vortex tube's cold outlet at higher pressures. For data analysis of the transient part, we'll have to first calculate Q air, Q load, and Q ambient. To find Q air and Q ambient, we'll have to numerically integrate the Q dot data over the entire data collection period using the sampling rate of half a second. To find Q load, we'll simply assume that the heat lost by the load is equal to its mass times specific heat times the change in temperature from the start to end of data collection. These calculations will be done using the R insulation values found from week 1 because these will produce more accurate experimental results than using the theoretical values. Using these calculated values, we can then find the discrepancy between Q air and Q load plus Q ambient and compare that to the uncertainty of Q total plus the uncertainty of Q air to draw conclusions about the system. If the discrepancy is much larger than the uncertainty, we would conclude that there is a large difference between the model and the real experiment, such as the large difference between the R insulation values we saw previously.